last one and the hardest one, A5. So now we've shown that that these cuts, that 0 is the identity, the additive identity. Now we need to show that every cut has an additive inverse. That means that for any alpha, there's some other number beta that equals 0. So for every alpha, there's some other cut that you add those together and you'll get 0. That's the additive inverse. So we have to prove that no matter what alpha is, this beta exists. So to do this, we're going to fix alpha in our set of cuts. So this is arbitrary, you pick one, but we're just going to fix it and we're going to stick with that alpha for the rest of this proof. Let beta be the set of all p with the following property. There exists an r greater than 0 such that minus p minus r is not in alpha. Okay. If you can glance at that and understand what the heck that means, you're a better person than I am. This is more of that incredibly painful arithmetic that real analysis is full of, that takes so much effort to understand it. At least for me, this stuff just doesn't jump out at me what this means. So I think the way to look at this is, let's think about what we need to have here. We have a set, alpha. Let's say it's positive for now. This is 0. So we're sort of saying that this cut sort of represents this number, alpha, whatever that is, right? Number is in quotes. What is the additive inverse of a number? It's the minus of this number, right? So it's an equal distance from 0 on the other side. So there needs to be some other number here, so that if you add these together, they come up to 0. So that conceptually what we need is to show that this cut exists, that there is a cut, so that if we take alpha and add it to beta, we're going to end up with the 0 cut. That's still incredibly hard to wrap your head around because what we're talking about is subsets here. So that means that what we really mean is that for all r in alpha plus all s in beta, all those numbers together, that set is all the negative numbers. So what we need then is what we're doing here. So we started with p is in beta. So p is some number here. What's minus p? So minus p is going to be on the other side of 0, and we're just hypothesizing that the boundary of beta is equidistant from 0 on the opposite side of 0, right? So if this is just a little bit more than beta, then minus p is going to be just a little bit bigger than alpha. So we got that. If p is in beta, then minus p is surely not in alpha. That's fine. But what's this minus r? So minus r is bigger than 0. So what we're saying here, if we think in terms of the way that we think about these subsets, we're saying that it's always about being able to get smaller, that nothing is definite. There's always room for another number in here. So what we're saying is that there's going to be some r bigger than 0 that we can subtract from p and still be within this gap. So if we subtract r here, r is not the full thing, but r might stop here. So then minus p minus r is going to land in there somewhere. So what we're saying is that that p then can get closer and closer and closer to this boundary. There's no largest p in beta, right? So it can get closer and closer and closer. That means that it's going to get closer and closer here to alpha. But no matter how close it gets, there's still always going to be an r that you can subtract and still land before the boundary of alpha. That's what beta is. Okay, so in other words, for any p in beta, some rational number smaller than the inverse of p fails to be in alpha, right? So no matter what p is, there's going to be some number smaller than p, than the inverse of p, that still is outside of alpha. That's what we're saying. That's what this means. Okay, so now again, we've defined this number. Once again, now we need to show that beta is a cut. That's the first order of business, and then we'll have to show that in fact alpha plus beta equals 0. So to show it's a cut, we have to show it follows the 3 properties. So 1, not empty, not all the rationals. So if we start with a s that's not in alpha, and p equals minus s minus 1. So what do we have here? So we're saying that there's some s up here that's not in alpha. That means that the inverse of s is going to be way over here in beta, minus 1. So it's going to be, here's minus s, and then minus s minus 1 is even farther over. So if we make this our p for this part. So if we say that this is our p, then minus p minus 1 is not in alpha, because then we have over here, this is s plus 1, right? The inverse of this is s plus 1, or minus p, right? Because p is minus s minus 1, so minus p is s plus 1. So this is definitely not in alpha. But then if we subtract 1 from it, we just end up back on s. So we started with s, so we know that this number is still not in alpha. So minus p minus 1 is not in alpha. That shows that p is in beta, right? That's the definition of an element of beta. So beta is not empty, right? Because we just showed if you just pick anything that's not in alpha, we can make a p that's in beta. So beta is not empty. And if q is an element of alpha, then minus q is not in beta. And we know that alpha is not empty. So there is something exists, and if it is in alpha, then its inverse is not going to be in beta. You can see that if there's a q here, then the inverse is going to be over here somewhere. So it's clearly not going to be in beta. So it's not all of the rational numbers. So beta satisfies 1. Okay. For 2 and 3, pick p element of beta and pick an r greater than 0 so that minus p minus r is not an alpha. Okay, so we know that p is an element of beta. So we know that there is an r that will make this true. So just pick one of those. So for 2. So first we have to show that if there's an element of beta, we're talking about beta now. If there's an element of beta, and then we have some rational number that's less than p, then it's also going to be in beta. So if we start with if there's a q less than p, then minus q minus r is greater than minus p minus r. Okay, let's just make sure that that's true. So we start with q is less than p. So that means that if we multiply both sides by -1, we have that minus q is greater than minus p, and then add minus r to both sides, so minus q minus r is greater than minus p minus r. So we showed that minus q minus r is greater than minus p minus r. That means that minus q minus r is not in alpha. That is b, because that's our reformulation of 2, that if on alpha we're talking about. That if we have that minus p minus r is not in alpha, and we have something else bigger than that, then that's also not going to be in alpha. But if this is true, this again is the definition of beta, right? So that means that q is an element of beta, and that is 2. We started with a p in beta. We took some q less than p, and we showed that that means that q is also in beta. That's what 2 is. Okay, one more. So remember, 3 is that for any element of beta, there is another element larger than p that's also in beta. Okay, so we're going to start with, we're just going to take a value, say t equals p plus r divided by 2. Okay, so r is positive. We started with that. So this is also, so r divided by 2 is also positive, so t has to be bigger than p. So t is greater than p. And minus t minus r divided by 2 equals minus p minus r. Let's just verify that again. So we have that t equals p plus r divided by 2. So if we just multiply both sides by 1, we have minus t equals minus p minus r divided by 2. Then, interestingly, if we subtract r divided by 2 from both sides, we get minus t minus r divided by 2 equals minus p minus r divided by 2 minus r divided by 2. This is going to be r. So that just equals minus p minus r, right? R divided by 2 plus r divided by 2 is r. So what we showed is that minus t minus r divided by 2 equals minus p minus r. But we started with minus p minus r is not in alpha. This is not in alpha. So minus t minus r divided by 2 is not in alpha. So we just showed 3 because we started with an element of beta. Then we found an element that's bigger than that element. We found t that's greater than p, and we showed that it's still not in alpha, which means that t is an element of beta, right? Because if the inverse of the element minus some rational number larger than 0 is still not an alpha, that's the definition of an element of beta. So if we start with p and we define t in this way, then we're still going to be inside beta. That's 3. Okay. So we've shown that beta is a cut, or beta is an element of R. Okay, so what we're trying to show, what we need is, we're showing that alpha plus beta is going to equal 0. So the first thing we had to show was that this is even, in fact, an element of R. We've done that, so we're off to a good start. Now comes the hard part, or the harder part. This is, I think, as hard as it's going to get. So now we must show that alpha plus beta equals 0. So again, anytime we're showing that 2 sets are equal, we're going to show the inclusion in both ways. So 1, alpha plus beta is a subset of 0, and 2, 0 is a subset of alpha plus beta. Show those two things, and that means that they've got to be equal. So first we'll show the first inclusion. If R is an element of alpha and S is an element of beta, then minus S is not an element of alpha. Why is this true? We've got to use B again. So if S is in beta, that means that there's some x. There's some x with x greater than 0, such that minus S minus x is not in alpha. That's the definition of beta. That has to be true for S to be in beta. But if x is greater than 0, then minus x minus s minus x, this is bigger than 0, so this is going to be less than minus s. But we started with this is not an alpha, so if this is bigger, then this has to also not be an alpha. So that's what we needed. That's B. Okay, so minus s is not in alpha. That means that R has to be less than minus s because R is in alpha. If minus s isn't in alpha, then it has to be outside of alpha, so it's going to have to be bigger than R. That's A. So if R is less than minus s, if we take this over, that means that R plus s is less than 0, right? Move this over, R plus s is less than 0. That means that R plus s is an element of 0. Okay, good. And we started with R is an element of alpha and S is an element of beta. So R plus S is an element of alpha plus beta. So this is an element of alpha plus beta. And we just showed that now it also has to be an element of, if we start with an element of alpha plus beta, then we've shown it's also going to be an element of 0. That proves this one, that any element of alpha plus beta is an element of 0. Okay, that's the first part. Now, as I said, every step of this proof is harder than what came before it. So here we go. 2. Now we have to prove the other way, that anything in 0 is also going to be a subset of alpha plus beta. Okay, so to do this, I'm just going to show us a little bit, and then we're going to have to try to understand what we're doing here. So pick a V that's an element of 0 and put W equals minus V divided by 2. Okay, so V is some number less than 0. So V is negative, so W is going to be positive, but half as far from 0. So it's half as big and positive. So W is greater than 0. Okay, then there exists an integer n such that nw is an element of alpha, but n plus 1 w is not an element of alpha. Do you recognize what this is? This is the Archimedean property. And this is specifically the thing that we spent so much time on with the well-ordering principle, that not only is there some number that will put you, some integer that will put you past your target, but that there's a biggest one, so that if we have alpha here, right, this is some boundary, there's some integer, and then we have a little w here, which we don't know what it is, but there's going to be some integer that's going to put nw here, and then if you even add one more to n, you end up on the other side. That's what we spent a lot of time proving a few weeks ago. so that this would be in alpha and this is not in alpha. This is all versions of the Archimedean property, or results of the Archimedean, implications of the Archimedean property. So now let's put P equals minus n plus 2w. Okay, so this is yet more of this arithmetic that just seems baffling at first glance. One thing that's important to do is try not to overthink it. So let's think about what we were just doing and then see how this applies to it. So we just said that we have an alpha with an nw over here and n plus 1 w is outside of alpha. Now we have an n plus 2 w. Well, what would that be? That would be one more over here. And we're saying that the inverse of that is going to be over here somewhere, that equals P. And specifically, so now, can you see what we're doing? What we're doing here is, this is beta. We sort of did this a little bit earlier where we've established that this number is outside of alpha. So we're gonna make P something bigger than that. So then when we're gonna be able to subtract 1 and still know that we're still outside of alpha. So that this number is going to be in beta. That's what we're gonna have to, that's what we're having to show. So this is the justification of this, but now we're gonna have to do the math and see what's going on. So then P is an element of beta since minus P minus W is not an element of alpha. Okay, now where did this come from? Minus W. The important thing to understand here is that what we're doing here actually, the way I drew this is a little bit misleading because these are not 1 unit apart. They're W units apart. And then this is 2W past this one. So W can be arbitrarily small or arbitrarily big. But this might be, W might be very, very close to 0. So that NW would be here, NW plus N plus 1W there, and N plus 2W there. So no matter what W is, it might be very close. We still have this arrangement. So, but that doesn't tell us where we got the minus P minus W. So the point is that if this was P, we're not subtracting 1, we're subtracting 1 unit of W from P, from the inverse of P, and we're still going to be outside of alpha, okay? But let's do the algebra to make sure that that's true. So NW, so let me just write this down. So NW we have, N plus 1W is actually NW plus W, right, if you distribute. And N plus 2W is NW plus 2W, okay? So if P, our definition is that if P equals minus N plus 2W, then if we distribute that out, we have that P equals minus NW minus 2W. So then, let's take the inverse of both sides. So if we multiply both sides by minus 1, we have minus P equals NW plus 2W. So then if we subtract W from both sides, we have minus P minus W equals NW plus 2W minus W equals NW plus W, okay? And then if we sort of undistribute it, we end up with N plus 1 W, right? And what did we start with? We started with N plus 1 W is not in alpha. So N plus 1 W is not in alpha. That was what we started with using the Archimedean property. So minus P minus W looks baffling, but all it really is we just took all of this algebra and subtracted it out, and rearranged it and we end up with n plus 1 w. So minus p minus w equals n plus 1 w, which is what I said we were going to do from the beginning. We found one that was outside of alpha. We went one bigger, and then what we need to do is that guarantees us that then we can subtract one and get back to something that we still know is outside of alpha. And then we have that v equals nw plus p is an element of alpha plus beta. Now, where did we get this one? This is because we know that p is in beta. We know that nw is in alpha. That's what we started with. So we have that nw plus p is just an element of alpha plus beta, right? Why is v equal to nw plus p? So first of all, let me say, remember what we're working on here is we started with v is an element of 0, right? That means that v is negative. And what we're doing is we're showing the second inclusion, which is that 0 is a subset of alpha plus beta. So we're starting with an element of 0 and we're showing that it's in alpha plus beta. So we started with w equals minus v over 2. That implies just multiply both sides by 2 equals minus v. And then v equals, so multiply both sides by negative 1, v equals minus 2w. So this is crazy. Okay, so that's minus 2w. Now let's look at p. P equals minus n plus 2w, right? That's what we started with. So if we distribute that, we get that p equals minus nw minus 2w. Move this over to the other side, and we have that p plus nw equals minus 2w, and minus 2w equals v. So that's what we ended up with here, right? V equals p minus nw. Okay, so we did it because we started with v is an element of 0, and we just showed that if v is an element of n0, then it's also an element of alpha plus beta. So that was, the algebra was just crazy, just so confusing, but not difficult to follow, just really hard to wrap your head around what you're doing step by step. But okay, so we've shown that if v is an element of 0, then it's also an element of alpha plus beta. That's what we wanted to show there. So we did it. We showed that we have shown that alpha plus beta is a subset of 0, and 0 is a subset of alpha plus beta. Therefore, alpha plus beta equals 0. And finally, there's not enough room here. Let me put it on the page. Of course, we denote this beta by minus alpha. So alpha minus alpha equals 0.
Okay, here is the link to the first video in this chapter. Here is the link to the previous video. Here is the link to the next video. And click here to subscribe, and please join me on Patreon. The link to that is below in the description. Thank you.